back to Physics through Computational Thinking. In this video, we'll continue to learn about plotting and visual thinking. We'll learn about salient properties of functions and how to plot them, how to identify them from the plot. We'll also learn to do two-dimensional and three-dimensional plots for vector plots, streamlines, and contours. So let's go ahead and get started with this. Let's have a quick review of some salient properties of functions such as zeros, divergences, extrema, and asymptotes. Zero of a function is defined as a point where f of x vanishes. If x star is a zero of f of x, then f of x star is 0. For example, let's consider the function f of x equal to x square minus 3x plus 2. We factorize this function, we get f of x equal to x minus 2 times x minus 1. From this, you can straight away read that if fx is 0, then x star is either 2 or 1. So then x equal to 2 and x equal to 1 are zeros of f of x. Let's go ahead and plot it and verify that. You can see that when I make a plot of x minus 3x plus 2, this function parabola crosses x-axis at 1 and 2. That is where the function vanishes and coincides with the x-axis. Zeros are important for many things. Similarly, let's go to the next property, divergence. Divergence of a function is defined as a point x star. If x star is a point where this function diverges, then 1 over f of x has a 0 at that point. Let's take, for example, fx equal to 1 over x minus 2 times x minus 1. F of x has a divergence if 1 over f of x has a 0. So 1 over f of x is x minus 2 times x minus 1. Therefore, the divergence for this function happens at x equal to 2 and x equal to 1. Let's plot this function and verify the same. Over here you can see that when I plot this function, there's a divergence, the function diverges at x equal to 1, and also over here, and over here at x equal to 2, and also from the left hand side. So sometimes the divergences will be positive, sometimes they will be positive and negative depending on which side of the divergent point you are at. Extremas are another interesting property. Extrema is defined as a point x star where f of x star, f prime of x star vanishes. Now, in order to understand what kind of extrema it is, you need to do some more work. You need to find out the second derivative, and from the second derivative you can establish whether it has a minima at that point or a maximum at that point or a point of inflection. In this case, let's take the same function again, f of x equal to x square minus 3x plus 2. This is the simple example. Let's understand where is the maxima or a minima for this function. At this point, it's actually useful to complete the squares rather than factorize f of x. When you complete the squares for this function, you see that f of x becomes x minus 3 by 2 whole square minus 1 by 4. Now this function becomes minimum when x goes to 3 by 2. Let's go ahead and plot it and verify this. So when I plot this function, again you can see it has got a minima at x equal to 3 by 2. Similarly, asymptote is also a property of a function. An asymptote is a curve that a function f of x approaches arbitrarily close in some limit. For example, x goes to infinity, x goes to minus infinity, or x goes to 0. What happens to f of x in that limit? That is called asymptote. Asymptote is another curve which f of x, asymptote is a line which f of x approaches when x becomes arbitrarily close to some limit. A familiar example is f of x equal to 1 by x, which asymptotically approaches x-axis as x goes to infinity and asymptotically approaches y-axis as x goes to 0. Let's plot this and find out. So plot of 1 by x, as x goes to plus infinity, we see that the function f of x becomes arbitrarily close to the x-axis. In fact, in the limit x goes to infinity, it becomes parallel to the x-axis. Similarly, as x goes to 0, the function becomes arbitrarily close to y-axis, and in the limit x goes to 0, it becomes parallel to the y-axis. On the left hand side, x goes to minus infinity, the function becomes parallel to the x-axis, and x goes to 0, it becomes parallel to the y-axis. It approaches y-axis. So x-axis and y-axis are called asymptotes of 1 over x. X-axis is asymptote of 1 over x, in the limit x goes to plus infinity or minus infinity, and it is asymptote, y axis is asymptote of f of x or 1 over x as x goes to 0. We can further increase the range of this plot and see that they actually do become arbitrarily close, but they never actually meet. So the function f of x keeps on getting close and close to y axis, becomes arbitrarily close, but it never really intersects with it. So these were some of the salient properties of a function. We are going to study zeros, divergences, extremas, and asymptotes using some examples. Let's take the first example and understand properties of functions, zeros, asymptotes, divergences, etc. using these examples. First example is f of x equal to x times mod x. Can you find out what are the salient properties of this function? Let's go ahead and plot this function and find out what are the salient properties of this function. Where are the zeros, extremas, maximas, minimas, asymptotes, etc. So when I plot this function, for mod of x you can use absolute value of x. So the function I am plotting is x times absolute value of x. Absolute value is represented by abs, and I am plotting the range minus 4 to 4. So this function is x squared for positive x axis and minus x squared for negative x axis. So question is, where does it have a 0? Very clearly it has only one 0 and lies at x equal to 0. Where does it have? Is that the question is that 0 a maxima, minima, or a point of inflection? That will depend on what happens to the second derivative. In this case, we have got function to be flat over here. In fact, its slope is 0 at x equal to 0, and also the second derivative will turn out to be 0, so this will become a point of inflection. You can also plot x cube, and you will see, interestingly enough, that it has got similar kind of behavior as x cube. X cube is also a function which has got a point of inflection at x equal to 0. Let's take another example. Also, let's quickly review other properties. It does not have any asymptotes. The function diverges as x becomes very large or very small. It does not have any other divergence apart from divergence at x equal to plus infinity or minus infinity. It has only one 0, and that 0 is also a point of inflection. Let's take second example. Let's take the function absolute value of x to the power 1 by 3, and let's find out what is the domain of differentiability and continuity for this function. Is this function continuous and differentiable everywhere? To do that, let's go ahead and plot this function. When we plot this function, we see that it forms a cusp at x equal to 0. So first of all, is it continuous? It's clearly continuous on the left hand side, it's clearly continuous on the right hand side, but is it continuous at this point? That depends on if the function has the same limit as you approach it from left or as you approach it from right. Absolute value of x vanishes when you approach it from left or approach it from right, therefore absolute value to the power 1 by 3 also vanishes. So both the functions approach 0 from left and the left side and right side, from both directions the function evaluates to 0, therefore it is continuous at x equal to 0. But clearly it is not differentiable at x equal to 0 because the derivative over here has a large negative value and the derivative over here tends to have a large positive value. Therefore the function is not differentiable for at x equal to 0. It is differentiable for x less than 0, and it is differentiable for x greater than 0, but it is not differentiable at x equal to 0. In this case, the 0 is also at x equal to 0, but there is this is also a minima, but it's not an extremum point because f prime is not defined. You cannot say f prime of x equal to 0, but it's an absolute minimum value for the function at this point. It does not have any divergences apart from x equal to plus infinity and minus infinity. Let's take the next example. This time we'll work with a famous function called Lorentzian. Lorentzian is given by f of x equal to a square by x square plus a square. Let us find out what is the asymptotic behavior of this function, and at the same time also look at what are its other properties. So in order to do that, what we'll do is, since there's a parameter a, we'll also understand what the parameter a does using the manipulate construct. For that, I'm going to use the manipulate command. The manipulate, I will manipulate the parameter a in the range of 0.5 to 2, and I'll plot the function a square by x square plus a square in the range of -5 to 5. When I execute that, I get this frame. I can slide a and see what happens. The parameter a determines the width of this curve. Lorentzian is a curve which vanishes at plus infinity and minus infinity. As you increase or increase a, its width increases. So the parameter a determines the width of the Lorentzian. It has a maxima at x equal to 0. You can easily verify that the derivative of this at x equal to 0 vanishes, and also the second derivative is negative, and therefore it has got a maxima at x equal to 0. As the x goes to plus infinity or as x goes to minus infinity, the function gets arbitrarily close to the x-axis, therefore its asymptote is the x-axis. Now Lorentzian is an interesting function. Let's go ahead and take a look at another example, and we'll come back to Lorentzian in a moment. Let's take a look at the example where we take a function just like Lorentzian, but in the denominator we'll keep it x square minus a square than x square plus a square. When it is x square plus a square, it is a Lorentzian function. When it is x square minus a square, this function has divergence. Let's identify what the divergence is. We'll go ahead and plot this function, and you can go ahead and slide the slider a. As I slide a, I do this in steps because it takes a moment to plot. As I increase a, you see the point at which the divergence is happening also increases. In fact, divergence is exactly equal to x equal to plus a and minus a. So this is an example of a function which has got a divergence. It has asymptotes. For example, as a gets arbitrarily close to plus 1 in this particular case, because or x goes to arbitrarily close to a, in this case a is 1. As x goes arbitrarily close to a, this approaches the line x equal to a, which is parallel to the y-axis. Similarly, when x becomes arbitrarily close to a equal to minus 1, the function approaches the line x equal to minus 1, which is and gets arbitrarily close to it. So x equal to plus 1 and x equal to minus 1 are asymptotes for this function, and also x equal to 0, the x-axis, that is y equal to 0, is also an asymptote in the limit x goes to plus infinity and minus infinity. So this particular example, it has got three asymptotes: y equal to 0, x equal to plus a, and x equal to minus a. Let's go to the next example. Let's take the function fx equal to x minus 1 times x minus 2 divided by x and find its asymptotes. Let's go ahead and plot this function x minus 1, x minus 2 divided by x in the range -5 to 5. In order to find the asymptotes, we have to take a limit. So for example, for this function, if I take the limit x goes to 0, you see the denominator dominates, the numerator goes to a constant which is plus 2. So the function becomes 2 by x. It behaves like 1 over x in the small x limit. So its asymptote is y-axis in the small x limit. In the large x limit, this 1 and this 2 can be ignored, and I get x square. X square divided by x is approximated as x. So in the large x limit, its asymptote is x equal to y line, which is represented by this dashed curve. So we can find asymptotes by taking various limits. So plotting helps in visualizing and understanding what kind of limits I should take. Without plotting, you can still do this exercise, but it can be slightly harder. So with visualization and plotting, it becomes easier to understand various properties of the functions. Let's go ahead and take a look at another example. Again, this time we'll take a famous function called Gaussian. You may be familiar with this function. If not, Gaussian is given by exponential of minus x squared by a squared. Let's understand the salient properties of this function. So let's go ahead and plot it, this time with a manipulate, and we'll manipulate the parameter a in the range of 0.5 to 2. Let's go ahead and plot it. As I increase a, the width of the Gaussian increases. I've also plotted e to the power 1 over e line. This dashed line corresponds to 1 over e. This corresponds to the value of a by which time x squared by a squared has become 1. So as x starts from 0 outwards towards positive x or negative x, this point represents when x squared by a squared has reached 1. That is when the value of the function has dropped from its maximum to 1 over e, and that is the point which gives the width of the Gaussian, and this point is equal x. This point corresponds to x equal to a. Let's go ahead and compare this, because this is a falling off function. Let's go ahead and compare this with Lorentzian that we just plotted. So I'll add Lorentzian to this. Lorentzian was a squared by x squared plus a squared. Now let's go ahead and change a. You can do it yourself and play around with it. You can always see, no matter what the value of a is, Gaussian is falling off much faster compared to the Lorentzian. In fact, in the large x limit, Lorentzian behaves like 1 over x squared, while Gaussian falls off exponentially, or e to the power minus x squared, which is much faster than 1 over x squared. So Gaussian will always go to 0 faster than Lorentzian. That is the large x behavior, but for both of the functions, the maxima appears at x equal to 0, and both the functions have asymptote in the x goes to plus infinity or minus infinity as the x axis. Also, in the neighborhood of x equal to 0, both the functions Lorentzian and Gaussian behave like a inverted parabola. In order to see that, let's go ahead and plot 1 minus x squared over a squared. And we have to constrain the plot range. We can see the plot range is 0 to 1. There we go. And as I change a, you see the behavior of all the three functions, the parabola, the Lorentzian, and the Gaussian, is identical near x equal to 0. It's only as you go away from x equal to 0, you see the function behavior is changing. I can also add a parabola. Now my figure is complete. I can change a and see that the behavior always is identical near x equal to 0. The three functions, all of them behave quadratically near x equal to 0, and their behavior changes as x goes away from 0. The parabola diverges, Gaussian converges to 0 the fastest, Lorentzian also converges to 0 but slower than the Gaussian. Those were some of the examples where we studied salient properties of the functions. That will be all for today, and we'll continue with more interesting things next time.